Here we see an avocado being thrown upwards, and we will analyze the input of power during the throw. With the application tracker, we track a specific point on the avocado during its motion and provide a reference for distance with the blue calibration stick, which sets the width of the avocado to be 6.4 centimeters as measured. It will create data points for the avocado's motion in the y direction over time, and this leads us to first look at kinematics, making motion graphs using position, velocity, and acceleration over time. Using 3 lines of best fit, which are used to represent the trend of data during the throw, during free fall, and during the catch, we can get a more accurate recording of the avocado's motion during the video.
As the avocado was thrown into the air, the distance into the air grew proportionally with the way it fell. It can be seen in the graph that at about 2.15 seconds, the avocado reached its peak height and began falling back down due to gravity. How fast the avocado reached this max height can be due to how hard it was thrown or how much force was exerted on the avocado upwards. The avocado starts from rest at 0 meters per second. As the avocado approaches its maximum height, it begins to slow down due to the force of gravity. The velocity again reaches 0 meters per second once the avocado is at its maximum height. As the avocado falls, it gains speed downwards, transition from gravitational potential energy to kinetic energy, leading the avocado back towards Anna. Right before the avocado reaches Anna, the velocity is around negative 2.8 meters per second. Its velocity upon being caught is 0 meters per second at the end, as expected. The acceleration slope is pretty messy. This is due to distance measurements in the y direction being slightly off during the tracking. As the force of gravity overtakes the avocado, acceleration becomes negative. The accelerations calculated were about 17 meters per second squared for the first section, negative 10 meters per second squared for the second section, and 88 meters per second squared for the third section, due to how quickly the catch decreased the avocado's velocity, which is off the graph and therefore not included.
We can use the data input and trends from these graphs to understand the energy conversions taking place in the video. Using an energy lens, we can identify the highest and lowest points of both kinetic and potential energy and compare them to one another on a graph where time is on the x-axis. This will allow us to create a graph of total energy over time and help us find power, which is calculated as change in energy over change in time.
The slope of this kinetic energy in relation to time is how we can see what the power is equal to. The kinetic energy starts at 0 joules because it is not in motion. Once it is thrown, its kinetic energy is relatively large, but it reaches 0 again as the avocado reaches maximum height. After reaching this height, kinetic energy also increases because the avocado is gaining speed until Anna catches it, where kinetic energy becomes 0 again. Potential energy reaches its maximum when the avocado is at its maximum height. Because these two values are proportional. Potential energy increases steadily up until that point, max height, when Anna throws the avocado, and decreases when it begins to gain velocity in the negative y direction towards Anna. Mechanical energy is the total energy combination of kinetic energy and potential energy. Where kinetic energy is less, potential energy is more, and vice versa. At the beginning and end, the points indicate moments where neither potential nor kinetic energy was present. The avocado was at rest and the lowest point in the y direction in Anna's hand.
So we know that power is equal to the change in mechanical energy over time. So we use 2 points from the steepest part of our energy graph to follow the equation power equals change in energy divided by change in time. We got an answer which was 7.25 watts, which seems reasonable for the power output given by a light throw.
Finally, we can analyze the forces on the avocado during the throw that cause it to accelerate, as was shown in the kinematics graphs.
Here we drew several free body diagrams. The sum of the forces on the avocado at the point represented in the free body diagram is given by the mass of avocado multiplied by its acceleration. We know there is a force of gravity acting directly downward on the avocado, as well as a normal force aimed directly upward, which is provided by Anna's hand throwing it up into the air. We also calculated the normal force applied by Anna's hand. In order to do this, we used acceleration, which we had already found to be 17 meters per second squared, and multiplied it by the mass of the avocado, which is 0.2 kilograms. The product of these two equals 3.4 newtons, which is the net force. Seeing the vector sums diagram, we know that the normal force applied by Anna's hand will be given by subtracting the force of gravity on the avocado from this net force. So from this net force, we subtracted -2, which is the force of gravity, and we got our final answer, the normal force, to be 5.4 newtons.